Infinity. Most people think it's just one thing. It turns out there are different sizes of infinity. We're going to look at the groundbreaking work of German mathematician Georg Cantor, who was born in 1845. Cantor was the man who tamed infinity. His work was groundbreaking and at the time very controversial. Top mathematicians in his time, they thought, well, Kronecker thought he was a scientific charlatan, a corrupter of youth. He was a rival of Cantor's, in case you couldn't tell. Poincaré said about Cantor's ideas, they were a grave disease, a grave mathematical malady, a perverse pathological illness that will one day be cured. On the other hand, not everyone was so negative. Bertrand Russell said, one of the greatest intellects of the 19th century. Hilbert said, in German, Aus dem Paradies, das Cantor uns geschaffen, soll uns niemand vertreiben können. No one shall expel us from the paradise which Cantor has created. I think Hilbert was right about this. Cantor's work is now ubiquitous. In the undergraduate curriculum everywhere, people learn about Cantor's work. It's accepted by all mathematicians. Odds, evens, natural numbers, integers, including things like -1 and -10, all of them are the same size of infinity. Other sets are bigger. Real numbers, the interval from 0 to 1, it's a larger size of infinity. There are infinitely many sizes of infinity. Interestingly, dimension is much more complicated than infinity, and we'll get to that next time. Why are we talking about those ideas here? You see, his work is revolutionary and surprising. It's not paradoxical in a technical sense, but it really does contradict our naive ideas about infinity. Think about the hotel. You see, when you have something finite and you add something, the sets get bigger. But if you have something infinite and you add something, maybe it gets bigger, maybe not. Understanding Cantor's work gives you a greater appreciation for sets of numbers, how complicated the seemingly simple number line is. It gives you a better understanding of the numerical world. So who was Cantor? Most mathematicians know this, that Cantor tamed infinity, he figured out how it is that we should study it, and that Cantor went crazy. It's usually portrayed that these two things are related. It's not really quite so clear. Cantor was born in St. Petersburg, and he moved to Germany. He was an accomplished violinist, another connection between mathematics and music. He studied number theory at the University of Berlin, and became a professor at the University of Halle. He always wanted a more prestigious appointment than that. But he did become a full professor by the age of 34. He worked in number theory, and then he worked in trigonometric series, trigonometric sums. Those are used to study sound waves, another musical connection. It was during the period from 1874 to 1884 that he did his really important seminal work on infinity and on set theory. But then Cantor suffered his first bout of depression in 1884, after his groundbreaking work on infinity was done. He was hospitalized briefly. It was cyclic. It was chronic depression. There were probably some triggers. There were family matters. There was a conflict with mathematician Leopold Kronecker. There was an inability to solve a particular problem called the continuum hypothesis, which we'll discuss. He got out. He moved on academically. He lectured on things like philosophy. He actually dove into the controversy of it was Shakespeare or Bacon who wrote the Shakespearean works. He was quite stable. In 1899, then he moved back into the hospital, and then his youngest son died, and Cantor was really devastated. And until his death, he was in and out of the hospital with depression. He did very little academic work. He retired in 1913 and then died during the war in the hospital in 1918. So let's dig into his work on infinity. His fundamental insight was about the size of infinite sets. See, the problem is that if you have finite sets, you can count them. But if you have infinite sets, what does size mean? His solution is the idea of a one-to-one correspondence. See, with finite sets, you have two options if you want to think about the size. One is that you could count a finite set, 1, 2, 3, 4, 5. But your second option is to match it with a set whose size you already know. Say you're coaching a soccer team and you need to make sure you get 11 players out on the field. You see, you could send them out on the field and then count, or you could just know that your clipboard shows 11 positions. There's a goalie, there's a right wing, there's a center mid, there's a stopper. You just assign each player to one position and only one player to each position, and then you just send them out. And you automatically get 11 on the field. What's going on is mathematically you have a one-to-one correspondence between the starting soccer players and the positions. This matching idea means that nothing is missing. There's no doubling up going on. This matching is incredibly useful. Sometimes every day we do some matching things without bothering to count. Sometimes I say, pass out these worksheets, everyone take one. Here in the United States, we have Social Security numbers, and we sure hope there's a one-to-one correspondence, a one-to-one matching between workers and their Social Security numbers. If there are two people using the same Social Security number, that's a problem. If there's a worker without a Social Security number, that's also a problem. Now let's look at matching and what this says about infinite sets. You see, for finite sets, we have these two methods, counting or matching. For infinite sets, counting fails, you would count forever, but matching still works. Think back to the hotel. There's no vacancies, so there's a one-to-one matching, a one-to-one correspondence between the guests and their rooms. Can you add a new guest? Can you find a new matching? Yes, you can. You move the current guests down and the new person is matched with door number 1. See, there's an important difference here. In the finite case, some matchings don't work. A new guest is just left out. There's no room for them. Others do. Many work. See, you could have switched 2 rooms and still this matching would work. But what happens when the sets are the same size? See, if 2 sets have the same size, they have the same what we call cardinality. And 2 sets have the same size if it is possible to find a one-to-one correspondence between them. Now, we have to be careful. We're not saying that every matching is a one-to-one correspondence. We're saying that there is a one-to-one correspondence. To make sure we understand this, let's go back to the Hotel Infinity. Now, originally, infinitely many guests were matched with infinitely many rooms. Everybody was matched up perfectly. Each person has 1 room, each room has 1 person. And what happens when that new person arrives? See, the previous pairing isn't a one-to-one correspondence between the rooms and all of the guests with this new person. The new person is left out of that matching. Is there a one-to-one correspondence? Well, yes, there is. The new person goes in room 1. Everybody else matches to 1 room higher than before. Because there is a one-to-one correspondence, the set of hotel rooms and the set of guests, including the new one, has the same cardinality, has the same size. Let's pause for a second and make sure we understand this and think about the power of a one-to-one correspondence. It feels like a very simple idea. 2 sets, they're the same size, they're the same cardinality if you can match them up. It works for finite sets. It works for infinite sets. Once Cantor had this initial idea, he started to explore the implications of it. Mathematician John Maybury said of Cantor's work, "It is pregnant with consequences." What are those consequences? Let's start looking at infinite sets and asking, are they the same size or are they different? Let's look at the natural numbers. Are they the same cardinality as the even positive natural numbers? 2, 4, 6, 8, on and on? There's an obvious mapping when you map the even numbers to the natural numbers. You can just match 2 to 2, 4 to 4, 6 to 6. But you see, that's not a one-to-one correspondence. You see, some numbers are missed. The odds are missing in that. So is there another one that would work? No. It's not too hard to figure this out. You see, both lists are already in order. So we just put them in that order. We match 2 to 1, 4 to 2, 6 to 3. In general, 2n matches to n. The positives, evens, therefore, have the same cardinality as the naturals. It's the same size. We can match them up in a one-to-one manner. We call this countable. Any set which has a one-to-one correspondence, a one-to-one matching with the set of natural numbers, is countable. If we can essentially count them, match something up with 1, something with 2, something with 3, it's a countable set. Now, that's already a little bit weird. You see, the evens are a subset of the naturals. In fact, it is a proper subset. That means that some numbers are not in the subset. we match the full set with essentially half of it, the natural numbers with the evens. Finite sets don't work this way. Imagine there's some sort of secret Santa program at work, and you have 20 people who put their names in a hat, and then just 10 people draw one name out of the hat, and then the names are gone. That can't happen. There's no way to match all of the people with just half of the people, or in fact, any proper subset of all the people. With infinite sets, you can actually match up a proper subset with the entire set. In this case, you're matching the evens up with the natural numbers. Every natural number is matched with an even. Every even is matched with a natural number. Nothing is missed. There's no doubling up. The evens are, in some sense, half of the natural numbers, but they get matched up with all of the natural numbers. It would exactly be like 20 coworkers somehow being matched with just 10 of them. It's paradoxical. It's counterintuitive because it actually does work. Things are just different for infinite sets than they are for finite ones. So how about the integers? Remember, it's not 1, 2, 3, 4, but it also includes 0, -1, -2, all the way down. Can you match those up with the natural numbers? Again, the natural way doesn't work. You could match 1 with 1, 2 with 2, 3 with 3, but you're missing all of the negatives, and you're missing 0 as well. Here's one way to do it. You could match 1 with 0, and then 2 with 1, and then 3 with -1, 4 with 2, 5 with -2. See, in general, you could take the evens and take 2n and map it to n, and that would get all of the positives. And then you could take the odds, 2n plus 1, and map it to -n. Now, you can check. There's nothing missed, and there's nothing doubled up. This is indeed a one-to-one correspondence. You can sort of think of this as two infinite buses, end to end, and the passengers are just sent to the Hotel Infinity. What you're doing, in some sense, if you have those people lined up, is just zippering them together. Let's move on to other sets. So the evens are countable, the integers are too. How about the rationals, right? Rationals, you can always remember, it means fractions. Things like 1/4 and 3/16, -41 13ths. Comes from ratios, rationals, ratio. Now, there's infinitely many fractions, infinitely many rational numbers between 0 and 1. There's infinitely many between 1 and 2. You can't possibly match all of those up with just one copy of the natural numbers, can you? Yes, you can. In fact, we'll give you two arguments. The first argument, I'm going to talk about using infinite buses. The second argument, we'll dig into a little bit of prime factorization. So, first, let's show that the positive rationals are countable. So let's use a bus argument. Bus 1 has all of the fractions with 1 in the denominator, in order. 1/1, 2/1, 3/1, 4/1. Bus 2 has all the fractions with a 2 in the denominator that aren't already on bus 1. 1/2, 2/2, that's 1, that's on bus 1. 3/2, 5/2, 7/2. On bus 3 is all of the fractions with a 3 in the denominator that aren't already on bus 1 or 2. 1/3, 2/3, 4/3, 5/3. Just keep going. Every positive rational is on exactly one of these buses. 7/13 on bus number 13. It's actually in the 7th seat. 14/3, it's on bus 3. It's in some seat. You could just sort of count it out and skip all the ones which were on previous buses. For instance, 6/4, you have to do some simplification before you figure out what bus it's on. 6/4 is 3/2, and so that's on bus number 2. It's actually in seat number 2. You can view these in an infinite array where the rows are the denominators and the columns are the numerators. You remove all the numbers that aren't in lowest terms, and now it is sort of just like infinite buses. See, we can put these in order by backing up the buses a little bit, just like we did last time, and then following the arrows. You can just go from bus 1 down and from bus 2 down. To get the actual mapping from the natural numbers to the positive, you just count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. When we do this, here's what the mapping looks like. Going from the naturals to the rationals, 1 is matched with 1/1, 2 is matched with 2/1, 3 is matched with 1/2, 4, we have to go back to the first bus, matched with 3/1, 5 is matched with 3/2, 6 is matched with 1/3, 7, back to the first bus again, it's matched with 4/1, Each natural number maps to exactly one fraction. There's nothing missed. Every fraction is on one of those buses. Every fraction gets counted and matched with some natural number. Nothing is doubled up. So how do we do this with the negatives? Once we've put the positive rationals in order, we've created a one-to-one correspondence from the naturals, we can think about doing all of the rationals, the negatives and zero, and it becomes much easier. See, you just think of a zipper. On one side, we put all of the positive rational numbers. On the other side, you put 0 and then all of the negative rational numbers in the same order that the positives were done. They just have negatives now. And now we take those two and we just zipper them together. And we create one list. And you're done. It's a list containing every fraction exactly once. It is a map from the natural numbers to the rational numbers. It is a one-to-one correspondence, a perfect matching. So let's give the second argument. Now, as with infinitely many buses, we can also use prime factorization to solve this problem. See, this time the map is from the rationals to the natural numbers. So for any fraction, let's write it in lowest terms. So take out any common factors. And then I want you to map p over q, the fraction p over q. If it's positive, I want you to map it to 3 to the p, 5 to the q. If your fraction is negative, if you have negative p over q, we can map that to 2 times 3 to the p, 5 to the q. Now, it's important here that every rational number is mapped to exactly one natural number. And unique prime factorization tells us that we'll never double up. Now, there's a problem with this, that some of the natural numbers are missing. For instance, 7 never appears in this listing. So it's not a one-to-one correspondence. But there is a way to get around this problem. So intuitively, if we want to find a map from the rationals to the naturals that doesn't double up and doesn't miss any, let's either find out that the rationals are the same size or smaller than the naturals. Now, if you want to complete this proof, you need something extra. Ernst Schröder made the conjecture. His proof was wrong. Cantor thought he had proved it. His proof was also wrong. And Felix Bernstein finally finished the proof. The name of the theorem is now called the Cantor-Schröder-Bernstein theorem. There's an ingenious proof. We have too many paradoxes to get to take that detour. But essentially, it shows that if you have a mapping which maps from one set into the other that misses some but doesn't double up, and you have a mapping from one set back to the first, which again never doubles up but might miss some, then there is a one-to-one matching. This particular theorem in this case shows us that the rationals are countable, which is what we already proved. Evens, integers, even the rational numbers are countable. We can find a one-to-one correspondence between each of these sets and the natural numbers. You might start to think that all sets are countable. Think about it. To prove that a set is countable, you have to find some one-to-one correspondence. To prove that a set is not countable, that seems a lot harder. You have to show that there isn't a one-to-one correspondence. There doesn't exist such a correspondence. But if you did that, you'd prove that there's more than one size of infinity. And that's what Cantor did. We'll see that after the quick conundrum. Here's a really strange example of infinity. This is just a pool tube. I bought it at the pool store. If you know that it's also a musical instrument, if you swing it around, you get a note. Now, you might think that if you swing it faster, you get a higher note. You might think that there's an infinite continuum of notes. A little bit faster, you get a little bit higher note. And that's partially right. You do get an infinite string of notes, at least in theory, but it's not a continuum. Listen. It jumps up. It's actually discrete steps. It's a countably infinite sequence of notes. You see, both speed and length are important here. You only get notes with wavelengths that fit nicely inside of this tube. The wavelength of those? Well, if you think of this as 1 unit long, the wavelengths are 1, 1/2, 1/3, 1/4, 1/5, 1/6. In practice, you only get a few, but those are the numbers from the harmonic series. We saw those when we were stacking books. And that's where the name comes from. It comes from the connection with music. It's important in musical applications. Anything you can play on a bugle, which is just a tube, you can play on this. The same mathematics tells you that electrons can't have just energy and energy level. Those levels are discrete. This idea of discrete versus continuous, those are very different. Different sizes of infinity, as you'll see. So what's countable in addition to the notes that you can play on a pool tube, at least in theory? The natural numbers are countable, the evens, the integers, the rational numbers. Even the rational numbers have the same size, the same cardinality as the natural numbers. Now, despite the difficulty proving that no matching is a one-to-one correspondence, Cantor was able to prove the following result in 1874, that the real numbers, all of the numbers on the number line, are not countable. There is no matching between the naturals and the real numbers. There's no one-to-one correspondence. That is called Cantor diagonalization. This argument is really mind-bending and amazing. We can prove that it is not possible to find a one-to-one correspondence between these two sets. See, it's not good enough to just look for a possible correspondence and then look for a long time and then give up. That doesn't prove that you can't do it. Cantor proved that no matter how hard you try, you will necessarily fail. Now, the argument we're going to give today, it's not Cantor's original proof, but it's widely regarded as one of the most beautiful proofs in the undergraduate math curriculum. Still, 20-some years after I first learned this, every time I talk about this theorem, it makes me smile. So, we're going to play a little game called dodgeball. This is originally conceived by Ed Berger and Mike Starbird. They were trying to help illustrate Cantor's proof. So I actually want to play this with you at home. The rules go like this. You're trying to dodge me. You're trying to write down a line of 5 zeros and ones that don't match any of the sequences of zeros and ones that I'm going to write down. If you manage to dodge all of my sequences of numbers, you win. If one of my lines of 5 numbers matches with the one that you get, you lose. All right? I hope this is clear. So the order of play goes like this. First, I'm going to write down one sequence, 5 zeros and ones, and then you have to write down just the first number in your one sequence. And then I'm going to write down my second sequence, and you write down just the second number in yours. I'll do a third sequence, you write down the third number, the fourth, your fourth number, and then I'm going to write down my fifth and last sequence, and then you, as the last move of this game, get to write down your fifth number. All right, so again, you're trying to avoid my sequences. If your sequence ends up on this list, you lose. If you manage to dodge all of mine, then you win. This is more interesting if you have somebody to play with as well at home. So I encourage you to find somebody. All right, so here's my first sequence, 0, 1, 1, 0, 1. So now you get to choose your first number. What would you like your first number to be? Okay, we'll go with 1. It's very sly of you. Okay, my second sequence, 1, 1, 0, 1, 0. And your second number, you get to choose. You choose a 0, okay. Your third number, mine is 1, 0, 0, 1, 1. That's my third sequence, and you get to choose your third number. So you choose a 1. You're very good at this game. The fourth sequence, 1, 0, 1, 1, 0. And your fourth number? 0. You're really dodging me well. It's not looking so good for me. My fifth sequence, 1, 0, 1, 0, 1. And now you can choose 0 for the win. You see, I hope you found a strategy, and that strategy is something that will actually always work. In a winning strategy, the first choice is opposite the first number in my first sequence. And that way, no matter what happens after that, your sequence will dodge my first sequence. The first numbers are different. When we get to the second line, your second choice should be opposite of the second number in my second sequence. And then no matter what happens after that, your sequence will be different from my second sequence because the second numbers are different. You see, at each stage, the optimal strategy makes sure to avoid all of my sequences. In the end, your sequence doesn't match my, say, fourth sequence because the fourth numbers in the fourth sequences are different. Now, this isn't really that fun of a game. It's not particularly interesting, in part because I always lose this game, but there are other variations. So what if the sequence were 7 digits long instead of 5? You can still win that with the same strategy. What if it were 20 digits long? That's a fairly long and boring game, 20-digit numbers down, and each time you're choosing one of them. But the same exact strategy works. In the 17th row, you could choose a 17th digit, which is different from the 17th digit of my 17th number. And then you'd make sure that your choice was not matched up with the 17th one. You can do that with every single line. And now, here's where infinity comes in. What if the game had infinitely many digits? So you may be wondering, well, then the game would never finish. So let's consider it as a super task. If we can finish all of the infinite rounds of this game, who wins that? Well, you can still win that game. Right? You can write down sequences that miss the nth number at the nth place. To see what this has to do with real numbers and with cardinality, let's play dodgeball, but instead of playing with zeros and ones, let's play with decimals. So, suppose I give you an infinite list of real numbers in decimal form. Can you find a number that's not on my list? Can you dodge my infinite list? Sure, you can. It's actually the exact same thing, but now you have a little bit more freedom. Let's say maybe you like 5s and your second favorite number is 7. Okay, let's help you create a number that's definitely going to miss every one of my numbers, 1 digit at a time. So here's my list of numbers. That first number, you could look at the first digit to the right of the decimal. And if it's not a 5, you could write down a 5. And if it is a 5, you could write down a 7. It's an 8, and so you might start your number with a 5. The second number, let's look at the second digit to the right of the decimal, the hundredths place. The same rule. This time it is a 5, and so you might write down a 7. The third number, you can dodge it. The third digit in the third number is a 5. That looks like, so you would dodge that and you could put a 7 in there. The fourth number, that fourth number looks like it might be pi. The fourth digit to the right of the decimal is a 5, and so you dodge that with a 7. See, you're always able to choose a digit so that your number is different from mine on every level. Will your number be the same as the 15th one on my list? No. They're going to differ in the 15th digit after the decimal place. One is going to be a 5 and the other isn't. And you can do this forever. You can dodge every single number. It's a brilliant trick. No, but notice that there's some self-reference going on, this idea of self-reference that we return to again and again. You're dodging the nth number by dodging the nth number in the nth digit. The n refers both to the number on the list, where it is on the list, and which digit it is that you're avoiding. It's not that far from the barber not shaving those who shave themselves. And that's really the heart of the argument. Given any list of real numbers, you can write down a real number that is definitely not on that list. You use the list against itself, and you dodge it at every place value. So remember what the goal was, to prove that you cannot find a one-to-one correspondence between the natural numbers and the real numbers. To complete this argument, you work by contradiction. Suppose there were such a correspondence. Then number 1 would be matched with some real number. Number 2 would be matched with some other real number. Number 3 would be matched with another real number. You would have an infinite list of real numbers, and supposedly that would be a one-to-one correspondence, a perfect matching, where no real number appears twice in that list, but every real number does appear in the list. But that can't be. See, you can write down a number that isn't in that list. You can dodge me at every position. You can write down a single number, which can't be the first number, it can't be the second number, it can't be the third. That's the contradiction. No such list could be complete. The real numbers are not the same cardinality. They're not the same size as the natural numbers. The real numbers are not countable. And with that proof, we have found a bigger size of infinity, a new size of infinity. You might have an objection to this. If you're clever, you might think you see a way out of this. If you found a number that's not on my list, why don't we just fix that? We take your number and we put it as the first number in my list, and then we just move everything down like people in the hotel. What's wrong with that argument? You see, you can just rediagonalize. You can just play dodgeball with this new list, and you can find a different number that's missing from this new list. No matter what the list is, there will always be something missing. You can always win dodgeball. You can always find a real number that isn't on any list of real numbers, because the real numbers are uncountable. Here we started with just a seemingly very simple idea that while counting works when you're comparing finite sets, matching works for infinite sets and for finite sets. This idea of finding a one-to-one correspondence to compare different things, different sizes of sets which are infinite. This idea of cardinality. Among the consequences of this idea is that the cardinality of the real numbers is strictly greater than the cardinality of the naturals. There is more than one size of infinity. Next time, something even more mind-blowing. There are infinitely many sizes of infinity.